So as I said, we were at the point that we had an Hamiltonian, quantized Hamiltonian of the chain of masses with springs, which I call phonons, and we want to solve it. Okay, so let me just write down the Hamiltonian as first step. And in the previous lecture, we defined the Fourier transform. Okay. So what we are going to do now is simply taking the two parts of this Hamiltonian and Fourier transforming them. Nothing more, nothing less. In this case, I'm going to do the full calculation with all the details for two reasons. One, once in your life, you should see how it's done. And second, there are few subtle, small points, but still it's good to see them. In the continuing of this course, we'll see more and more Hamiltonians. I don't intend each time to go through the full derivation. You always can do it at home or ask from the teacher assistant to give you more details. But this one, although it's a bit tedious and a lot of black work, nevertheless, I'm going to do it in details. Okay, so I have two terms. First term, all I'm doing is taking the inverse transform and writing it down, nothing more.
One of
It's not touch, I guess.
One of the prime on the exponent should be on the k, rather than the x.
Yes,
In the exponent.
Exponent, just one moment.
It should be, I assume, the best.
Okay, now it's clear, right? All I do is take the definition, perhaps I'll write it down here in full, although we have seen it last time. Okay. We'll just copy it twice and write it down. Okay.
We're using pi.
Hi. Here. Someone is awake here. No dependence on x except for here, so I can perform this integral. The reason for k and minus k is because they have here the same sign. Okay, nothing earth-shattering. Second term. Just know, this is not the k of the Fourier transform, that's why it's denoted ks. Just don't get confused. Again, nothing beyond just using the definition and writing it down. Everything okay? You're looking a bit worried.
It's okay.
As I said, no magic, no tricks, just simple writing down the definition. Okay, the only place that I have an x dependence is here and here, so I can perform the derivative. At the end of the day, that's the only reason to do the Fourier transform. If you look at the original Hamiltonian, I have a derivative of an operator, not the most pleasant mathematical objects that you can have. Here, the derivative is not anymore on the operator, it's just on a usual exponential function. Right. I have minus because the derivative twice removed the I. So it's minus 1. Okay. This is our good old friend. The delta function?
Without tag. Minus k without tag.
Right. And
לא, עדיין שיחה שנקראים שונים.
actually, it should have a prime because it's not yet closed. Okay. So at this point, we can replace the Hamiltonian in the real space with the Hamiltonian in the Fourier transform space. Okay. Now we'll just define a frequency. can rewrite all this term.
You're missing half, maybe? במקום ה-L.
It's 2. It's supposed to be 2. Okay. This already reminds us an harmonic oscillator. Two differences, one important, one not so much. First of all, in the usual harmonic oscillator, we have here P operator square and X operator square. Here we have something a bit different. It's K and minus K, right, in each spot. Okay, let me start from the other point. The big difference is I have here, instead of one harmonic oscillator, how many harmonic oscillators?
K.
The number of K.
Infinity.
Infinity, basically. Countable infinity, but still infinity. The other problem, which is not a real problem, and we'll get rid of it, it's not independent at the moment. We have pairs, K and minus K. This with a bit of mathematical massaging that I'll do in a moment, we'll get rid of it. We'll have only one harmonic oscillator, which is uncoupled to all the other harmonic oscillators. The fact that we have infinity, indeed, we have an infinity number of harmonic oscillators. Not surprising, we started with an infinity number of degrees of freedom. What you did in your previous course, you started with two X and P, two independent variables, and ended up with one harmonic oscillator. Here we start with an infinity. We continue to have an infinity of harmonic oscillators. Once we get rid of this K and minus K, they are independent, and we can solve each one of them by itself, so life looks promising. Okay. So, I'm now going to spend too much time on getting rid of the K and minus K, but as I said, once in a lifetime you should see it. But we will solve it the same way that we solved in a harmonic oscillator in the third in your undergraduate course. Again, very similar to the usual harmonic oscillator. The only difference here, we have to use K and
K,
minus.
K tag K. K tag K.
A dagger.
K dagger.
A dagger K. Okay, just to feel comfortable with it, let's check the commutation relation. Just wrote all the commutation relations. Come in here. Okay. Has to be 0. Because it's always commutation relations. If it's not the same K, of course it's 0. If it's the same K, it's still between the same operator, and therefore has to be 0. Don't have to worry about it. Check the commutation relations that we wrote last lecture. And we end up here with as expected. The same way, I'm just filling up whiteboards for no reason to show it. Okay. Just reading off these definitions, just writing the inverse. Sometimes instead of writing phi of minus k, it's customary to write phi dagger k. At the end of the day, the whole difference between k and minus k will be the sign here. Remember, the only place that k comes in is in the linear definition of omega k. Not surprising is they're switching the plus and minus. Okay. Now what we are going to do, take these definitions and enter them here. Okay, so when we switch the boards, we'll be able to see this one. Okay, that's from the first term. Why is there a minus here? Because of the I came from here.
I think that in the momentum dagger, it should be reverse sign, and in the AK, just if you make a complex
Here's
composite,
something.
yeah, in the A dagger should be, I think, minus sign, and in overall minus sign.
That one I think that not, but check and let me know. I think that there's no overall minus sign. Okay, so we have here 4 terms. Let's move to this part. So I'll just use this m omega k squared over 2 instead of this constant. Okay. So here we have an overall minus sign. So basically, I would like to get rid of these two, which I've marked in red. The problem is, it's k and minus k. Here it's minus k and k. Is that a problem?
It commutes.
No, I want to show that they are equal, and this is a minus sign, and this is a plus sign. And I'm not...
Yeah.
The things that... The easiest way to get rid of them, k goes from minus infinity to infinity. So the order that I do the summation doesn't matter. So here I'm going from minus infinity to infinity. Here's the other way around. Therefore, can get rid of this and this. Can get rid of this and this. As if I'm summing from the other way around. So this and this is the same, this and this is the same. Because minus k here is equal to this guy. And I'm ending up with Yes.
Why do they cancel? You have a plus.
Which
and-
one? These?
Whichever.
יש מינוס.
These have minuses between them.
There's a plus there. Plus. Ah, okay.
From our eye somewhere there. So these guys fall off. These here the minuses become pluses. And since I reverse the order of summation on k, so the minus k is equal to k.
Thank you.
So they are here it's dagger. The first is a dagger, the second is not a dagger, and here again reversed, so it's non-dagger dagger. So two terms for written here. So we spent quite some time tidying up this k's and minus k problem, but we see that in the end of the day we have here independent harmonic oscillators, a set of infinite number of independent harmonic oscillators. And we'll end up by finally using the commutation relation. Without the case, you're well familiar with it from the regular harmonic oscillator. And we can rewrite it Okay, so congratulations. You solved your first problem in field theory. So what's the solution, basically? Let's stop for a moment and remind ourselves what is the solution without the k. Okay, so call it simple one particle whatever harmonic oscillator. Okay, the solution was the energy is a quantized number where n goes from 0 to infinity. And we had eigenvectors of n and energies corresponding to n omega plus half. Pay attention here, I didn't use h bar. You won't fill it up throughout the whole calculation. Oh,
Can you say again, what does it say? N equals to something
0, 1, 2,
okay,
till
okay.
infinity.
Okay. So,
Okay. Exactly the same logic corresponds to the result that we have achieved here. The only thing that change is I have now an index that goes from 0, 1, so on, k. Okay, at this point you should start throwing objects at me.
Yeah, there is an infinite from
There's, my result tells me there's infinite energy because I don't care about what's happening here. This summation over all k's will give me infinity. Welcome to the exciting life of field theory. There's always infinities. But why I'm not so worried, at least on the pedestrian, on the everyday use level, because I never care what is the overall energy of a state. I care what is the difference in energy between different states. And when I want to define here a state, I'll write it in the following way. Okay, I'll tell you. How many quantas of energy I have here? How many quantas of energy I have here?
infinite.
No, quantas. Meaning, if I'm going, let's adopt this notation. I didn't define the notation, but I think it's very clear. The same kind that I had here, it's in the 0 state, 1 state, 2 state, and so forth. Here I'm asking for the first k, what is the state? For the second k, what is the state? And so on and so forth. I wrote only the positive case for brevity, But of course, for each k, I can have a minus k. And I also can say how many quantas of energy I have in this negative state, and just it's easier for me just to cut it off and write only the positive. And what does it tell me to do? It tells me, okay, you want to know how much energy is in this state. That's the result that I obtained. Now, you say, well, I've added another quanta of energy at state k equal 2. It's not really 2, it will be 2 times pi over the size of the system L, the usual way I discretize my Fourier transform. But for the moment, let's leave it. So it's a different state, which has a different energy. The difference between the two energy states is just omega of k equal 2. Give me another state. I'll write down the energy. I can subtract and get the difference of energy to the other state, and so on. So I don't know how to get rid of this guy. But this guy appears in all of those states. So it's some infinite that I don't know what to do with it. But on the other hand, I can always define the energy states of the system compared to some other state in the system. Okay, that's one conclusion that we can draw. The other conclusion that we can draw from it, we basically wrote down the eigenstates of this field. Right? Basically, what are the eigenstates? Tell me how many quantas of energy exist for every k. K equals 0, 3, k equal 1, 20, and so on and so forth. That's an eigenstate. has an energy. Know how to calculate it. And now I'll do the final jump. Where are all the properties of my original chain? We had a chain with a spring constant. It had the objects there had mass. Where did all this go? The only place that it went into is here.
What do you mean?
Well, do I have it here? Oh, here. I'll rewrite it. All the properties Ks and A, all of them go into this dispersion relation between omega and K. They are not the properties of the quantas of energies that appear here. They just define a dispersion relation. And the dispersion relation is linear. The smaller the K, less energy it costs me to create such a particle. And basically, I can create a particle with as small energy as I want, as long as my system becomes infinity, because that's the quantization of K there. So, basically, now we have all the building blocks to introduce a particle in field theory. Yeah.
Does it mean that there is an infinite number of particles in K equals 0?
Basically, if I have a state K equals 0, it doesn't play any roles there. Okay? It's basically meaningless. If you think about, or if you want to look at on it the other way around, that's part of its contribution. So, let's introduce a friend that we met in the course of condensed matter in your undergraduate studies. It's a phonon. Basically, what do we know about the phonon? If it's an acoustical phonon, this is the dispersion relation. Fine. We call it a boson. Why? Because I can have an infinite number of phonons at the same quantum number K. Unlike fermions. And it's a massless particle. Why is it massless? Because in principle, I can add a phonon to this system with k that is close to 0 as I want, I don't have a minimum amount of energy in order to add a new particle. If I add, let's say, an electron to your system, we know that even if it's at k equals 0, you have to pay mass, right? Here you can add at k equals 0 a particle that doesn't cost you energy, meaning it has no mass. Okay, and the big conceptual leap in field theory is telling you basically every particle that you see around you has its origin in some field theory that has a quantized field, and its properties come out of solving the Hamiltonian or Lagrangian of that field theory. It's not necessarily to come out with some model of why this field exists. If you remember here, the logic behind this field was that I looked on a system of masses and springs and so on and so forth. But once we got through the solution, the properties don't depend on these details. It's only some constant that comes into here. The fact that it's boson, the fact that it's everything that I know about the system doesn't depend on these microscopical details. And nowadays, if I go and write a field for an electron, I don't necessarily come and explain why I took a Hamiltonian with a certain form. It's a field. This field has the particles. In this case, it's a one-dimensional massless boson, known as a acoustical phonon. And that's it. So instead of thinking I'm writing a Hamiltonian for an electron, I'm writing a Hamiltonian for the phonon, I'm writing a Hamiltonian for a photon, so on, I'm quantizing a field that gives me the properties of the particles that I see. Okay, and to make this clearer, let's see how I take this Hamiltonian. Where is it? Here. And add a mass term. Not the mass of the particles that compose this chain, but the mass of this field that will give me excitations that will cost me energy to create them each time I add a quanta of energy to this field. Okay, so the last part will be doing exactly this. So still have these two terms. Okay, all I do is add a phi square term to the Hamiltonian.
Inside the integral?
Yeah, all the continues. Instead of having terms of only pi square and derivative of the field, I'm adding a term which depends on the field itself. Now, if you're very ingenious, you can go and try to think how you would push such a term into the springs and masses that we started this Hamiltonian. Is it important? No. All I need to know is now I'm writing a field with this Hamiltonian or the corresponding Lagrangian.
Where did you get the field from?
Here.
No, so is this the only field you have?
No.
So you're just guessing fields and trying to solve?
Exactly. You come and what you are really doing in field theory on the level of let's call it the most deep level of it, you are coming and asking myself, okay, what number of fields? I can have additional fields here, not only phi. What form can the Lagrangian or the Hamiltonian take? Can come and tell me, oh, I want to add here a phi to the fourth. Towards the end of the course, hopefully we'll get to a point where we'll deal with a phi to the fourth. If I'll try to add here something to the power of 3 or any odd, see that the whole, it doesn't work. Okay, so I'm coming and telling, oh, why is this only to the square and not to the fourth? Good, you want to add to the fourth? See what are the properties, check with your fellow experimentalist. Do you see any particle that behaves like this? Yes, great, I explained something. No, well, that was a dead end. And basically, the whole, in very simplistic terms, all the standard models that you have nowadays in field theory is adding a bunch of fields, a bunch of Lagrangians, telling with this bunch of fields and with this bunch of Lagrangians, it can solve everything that I see around me. Then you can sit and say, well, I want to add another symmetry to the Lagrangian, the supersymmetry. For every term that I have there, bosonic and fermionic field, I want to invert them. And 30 years ago, people would come and say, that's a great idea. There's no real reason why I will have a certain structure of a Hamiltonian or Lagrangian with these bosonic and these fermionic fields, and why wouldn't I have the opposite? You go, you solve, you get some very nice results. It answers even a few puzzles. I won't go into which puzzles. You tell your friends, okay, let's build a huge collider around Genève and go and try to measure them. 30 years after it, you see nothing. And then either you say, well, I don't know why, but my guess, it looks so elegant that you can replace bosons and fermions with supersymmetry. Nature, for some reason, doesn't want to follow it. So I have to go back and think perhaps there's another principle that determines which Lagrangians exist and which fields exist. Or I go and say something like, well, you saw there are, at the end of the day, some constants that I put here. The constant for this supersymmetry is so big that I'm not able to see it with the current collider. Let's build something 10 times more energetic. Hopefully we'll see it then. Because I have no good reason to determine what is this parameter. And basically, it worked very well till we got to the point where we had this the standard model, and people thought that we can continue with this type of logic. Let's look what is the symmetry and add terms of the symmetry will be fulfilled. Now we are at a point that we don't have a good idea how to progress with it. Okay, so you can look on it as a huge problem in physics. You can look on it as a huge opportunity in physics. If you go back historically, you go back 120 years, and you had no idea why a hydrogen atom puts out light only in a certain spectrum. Okay, but that's a game. So, 1 and 2 we did. Let's see what happens if we add 3. So I'm looking only on this term. Okay, the whole bag of tricks that we did before, and we end up let's see if I have it. But you see, that's the same structure of terms that we had from here. Not the same constant, no k-squared dependence. but everything else is the same. So, my Hamiltonian is same result as before. The only thing that changes and even for k going to 0, it costs you some energy to add this particle. So instead of a massless boson field, we got here a field with a mass where the energy to add another boson costs you some proportional to omega 0. That was fun. The main reason that it was fun is that still we have k independent particle oscillators, or if you want, particles.
So it gives the help that we had to energy the last time.
What it tells you is basically the spectrum, the relation between k and the energy is not linear anymore. At small k's, it's just the omega 0. At larger k's, it returns to the previous dependency. Which means that if you're dealing only with small k's, just adding a particle mainly costs you omega 0. In a paraphrase, it just costs you mass. Adding a particle, the main contribution is the mass. Actually, what happens for an electron? To create an electron, most of your energy goes into creating the mass of the energy. At small k's, it's not so important what's the k. That's basically what it is telling. Still, it was a free phone. What kind of phonon is this? Actually, what you have studied in an optical phonon. If you would want to go back and create a springs and masses model, which will give you this type of Hamiltonian, you'll go and do it by having two different masses in each odd or even lattice point. But from the point of view of fields, I don't care what model gives you this type of Hamiltonian, which microscopic model. If you want, it's like going back to Maxwell, who when he started to describe electromagnetic fields, he put in all kinds of cogs and levers into the ether to explain what's happening there. Nowadays, we just write the fields, the electromagnetic fields. We don't build a mechanical model that gives you such behavior. The same here. I started from a model of springs and masses, but in the end of the day, what's really important for me is the form of the Hamiltonian. If I'll go here and add a phi-force term, then I won't get independent oscillators. They'll be dependent, meaning they will be interacting particles, which makes life harder to solve. We will be able to do it with perturbation, not a full and clean solution as we got here. So, what we'll do in the next lecture is basically extend this type of model and see, for example, how can I get out of a different field charge. What do I have to add? This model has no charge. I can create or destroy quantas of energy however I want. Charge tells me that I have something conserved. And that we'll do in the next lecture. Okay, questions? Okay, so we'll stop here.
Okay, thank you.